Hello everyone, we are going to figure out how to solve problem number 4 from your homework packet. So it says 3 positive particles of charge 17 microcoulomb, that's 10 to the minus 6 coulombs, are located at the corners of an equilateral triangle of side D equals 25 centimeters. Calculate the magnitude and direction of the net force on each particle. So it's going to be the same for each particle, Q1, Q2, and Q3, so we'll focus on, let's say, Q1 at the top of that triangle. The first thing to notice is that this problem can be broken up into two problems, a lot simpler. At first, we simply have Q1 right here. Let's turn the pen on, that'll work a little better. We have Q1 right here, and it is feeling an electrostatic repulsion from Q3 down here as well as Q2 down here. We can first look at the problem of having Q1 17 microcoulombs repulsed by Q3 also 17 microcoulombs 25 centimeters away. To solve this kind of thing, we would use Coulomb's law. So we would say the force of repulsion equals K, a constant, 9 times 10 to the 9, or 9 billion, times Q1, Q2 divided by R squared. So we'll fill in 9 times 10 to the 9 for K, and 17 microcoulombs for both Q1 and Q2. For R squared, which represents the distance between the charges, we're going to use 25 centimeters. Of course, in this class, we don't use 25 centimeters. We always use meters. So we're going to say instead 0.25 meters. Plugging this into your calculator now. You should get a force of 41.6 newtons. Okay. Let's make that work. There we go, a little bit better. 41.6 newtons. That represents the force that Q1 feels from Q3. That'll be off in a, let's say, northeastern direction. I'm sorry, northwestern. From Q2, it'll be the same, and it'll feel that in a northeastern direction. So now we can imagine Q1, this is our charge, and it feels a force in this direction of 41.6, and similarly, a force of 41.6 in this other direction. Now, if you think about the geometry of the problem, we have an equilateral triangle. That means every one of those angles inside the triangle is 60 degrees because they all have to add up to 180, so 60 times 3 makes 180. That means when we're looking at our triangle that we've created with our forces, and we say that this angle down here is 60, that means the angle between the two forces will be 60, or if we want to cut it in half and say right here, it'll be 30 degrees so that we can create a nice right triangle. So what we're interested in is going to be this resultant force that comes up from these two vectors. Of course, now you're seeing an angle, you're seeing some numbers, you're hearing about resultant force, you're hopefully thinking of trigonometry. So how do we decide if we need sine, cosine, or tangent? Well, think about what you have and what you want. So what we have is 41.6. On that triangle over there, the 30-degree one, you can see that that represents a hypotenuse. So we have a hypotenuse of 41.6. And what are we looking for? We're looking for that piece that's pointing directly up away from the 30-degree symbol right there. Well, that's going to represent adjacent. So what do we want? adjacent. Now think about which trigonometric function correlates hypotenuse and adjacent together. That would be cosine. Remember that cosine of theta equals adjacent over hypotenuse. So solving for adjacent, we'll say hypotenuse 41.6 times the cosine of 30 degrees, which will give you 36 newtons. That's just a component from one of those vectors though. We have two of them, so we'll double that and get 72 newtons total for our force directed upwards.